Okay, it's 12 o'clock, so let's get started for today. Just having a look at the calendar there now. So it's November the 20th, we're like less than 2 weeks out, so we're totally in the home stretch now. Not lots of time left. So we'll keep muddling through and do our best. You had your test on Friday. It is not marked yet. I started this morning, and I got through kind of question 1, part 1, and I got the TA started on his share of the marking. So I don't have an overall sense of how everybody did because I only just got started. So before we start for today, does anybody have any questions about anything? Okay, so last day we talked about resistors in parallel, we did combination circuits, we did Kirchhoff's laws, we talked about the current law, which was conservation of charge, and we talked about the potential law, which is conservation of energy. We're going to do more of these examples today, and then we should be able to move on to RC circuits. So our first example of the day, let's have a circuit that looks like this. The reason I picked this circuit is because this is one we would not be able to do with equivalent circuits. We've got our 2 batteries. You can't break this down like the other ones. It's just not a simple circuit. So the way to solve this one is with Kirchhoff's laws. So let's start with our strategy. So the first thing we'll do is we'll draw and identify all of the currents in the circuit. So that's going to be step 1, is to identify the currents. I'm going to say that this is going to be my battery 1. So I'm going to say that current 1 comes out of the positive end of this battery. I'll label that current 1. If we like the idea of labeling the batteries, the high potential end and the low potential end, current is flowing through from left to right. Current flows from high potential to low potential, so we can label our battery ends if we like. The current gets to point A. There are 2 branches it can travel through, so the current needs to split. Part will go through this resistor and come down through this branch, and part will come down through this resistor. I'm going to call this current I3. And now we get to something interesting, and this goes back to a question last day, which is how do we know what direction to draw things? Okay, that's a really good question. I said when we get to part A, the current splits, and part goes down here and part goes this way. So I could draw the current going through that way, that's fine. But I've also said that current comes out of the positive end of the battery. Okay, so now I've got 2 conflicting ideas. What I have to do is I have to pick one way or the other and I have to draw it. Then I'm going to think ahead. When I get an answer, if I've picked the correct direction for my current, my answer is going to be positive. If I've picked the incorrect direction, my answer is going to be negative. I can't really tell by looking at this problem which way it's going to go. I just can't do all those numbers in my head, so I have to pick one or the other. I'm going to stick with my convention of picking positive terminal where the current comes out. I'm going to label this I2. If instead I had labeled it the other way, then I might get a negative for my answer. So if I'm right for this direction, my answer is going to be positive. If I'm wrong, it's going to be negative. So that's something to be aware of as you're doing these problems. Okay, so now I've got a current in each branch. So this is also I1. This is also I3. And this is also I2. Right, that's nicely, clearly labeled. So I've identified all of my currents. I'm also going to identify my loops so that I can write down my potential law. So I'll identify 2 loops. Loop 1, I'm going to take coming around this way. The question we had last day was how do you know what direction to draw your loops? The true answer is it doesn't matter because the math will all shake out in the end. The convenient answer is, as much as you can, have your loop direction match your current direction. It just makes the equations easier to follow. So this one is pretty straightforward. I'm going to take my loop direction to come around this way. And I'm going to call this loop 1. Oh, and we dropped the ball when we were labeling our resistors. So I3 comes from top to bottom. The top is high potential, the low is, the bottom end is low potential. I2 comes from left to right, so from positive to negative. For my next loop, I'll come over here. So again, I'm going to take my loop to match my current direction, just because it's going to make things easier as I go through the process. Okay, so we've shown our currents, we've shown our loops. Next, we write down our laws, the current law and the potential law. So for our current law, what we know is that the net current into a junction equals the net current out of a junction. So let's identify a junction. Let's pick A, it's already labeled for us. So let's write the current law at junction A. So at A, the net current going into A is I1 comes in from the left, I2 comes in from the right. So I1 plus I2 equals I3. So current in equals current out. So for our loop rules, we've got our 2 loops, loop 1 and loop 2. At loop 1, the loop rule says that the net potential around any closed loop has to sum to 0. Some potentials will be positive, some potentials will be negative. As we come around our loop 1, let's see. So the rule of thumb, if you don't like the labeling of the resistors as positive and negative, so if you don't care for that approach, if your loop direction matches your current direction, so if things sort of are all going in the same way, that means you get a potential increase with a battery and a decrease over a resistor. So that's a rule of thumb you can follow. If the loop direction is opposite your current, then things act in the opposite way. You get a decrease through the battery and an increase with the resistors. So either approach. So let's come around our loop. We'll start with the battery. So we go from negative to positive, a potential increase. So plus 12 volts. Just so the equations don't look so messy, I'm not going to include my units on this step. Typically I do include them, but today I'm not. Then I hit the 3.9 ohm resistor, so my loop and my current match directions. I get a drop across the resistor. That makes sense. I go from high potential to low. My potential difference across a resistor, V equals IR. So my resistance is 3.9 ohms, and my current is I1. So we're using Ohm's law, V equals IR. I get to my next resistor. My potential across this resistor is current I3 times the resistance. My loop matches my current, so it's a potential drop, or I go from high to low. So minus 1.2 ohms times I3. The next resistor is the 9.8 ohms. The loop and the current match, so it's a potential drop. It goes from high potential to low potential. So minus 9.8 times I1. Sum of that potential has to be 0. Are we good with that equation? Yeah.
Just a quick question. Is it possible? Is it possible to remove that resistor at the bottom? And why is there 2 different current values down there?
So the current that goes through this one is current I1. Okay, so current I1 goes through this resistor and this resistor. And current I3 goes through this resistor. These 2 currents are different because it's a different branch. Does that answer your question?
What about I2?
So I2 is a different branch still, so this one has to have a different current than these 2. So every branch has its own current.
Okay, so I could just see them as 2 different sections?
They're 2 different sections of the circuit. Ultimately, they're all connected through these equations, but they're different pieces, so they have different currents, yes. Yep.
Well, just one last question.
Yep.
So I2 doesn't come out of the positive end of 9.8 for your resistor?
So current I2, we can think of it coming out of this battery. So this battery outputs a current, this battery outputs a current, and then they sort of combine over here. We can think of it that way. Okay, I'm just going to simplify this equation a little bit. I've got 3.9 I1 and 9.8 I1, so I can combine those two terms. So 12 subtract 13.7 I1 minus 1.2 I3 equals 0. Okay, at this point I can't do anything. I've got three unknowns, I've got two equations, so I need to do a little bit more work. I need more information. That more information comes from loop 2. So I'm going to write my loop rule for loop 2. So at loop 2, I'm going to start with my battery. So coming around my loop and my current match directions, I get a potential supplied by the battery of 9 volts. So plus 9 volts, from negative to positive, low to high, that's potential increase. I get a decrease across my 6.7 ohm resistor. The potential is the current times the resistance. So minus 6.7 times I2. And then the next one in the loop is the 1.2 ohm resistor. That's got a current of I3 running through it. So it's minus 1.2 times I3 equals 0. So there's my loop rule for loop 2. When I take stock of what I have now, sorry, excuse me. I have three things that I don't know. I have three equations. I can solve this. So my algebraic approach is going to be, I'm going to rearrange this one to say I1 equals something in terms of I3. I'm going to rearrange this one, I2 equals something in terms of I3. I'm going to pop both of those things up here, and I'm going to solve for I3. Then I'm going to come back here and solve for I1 and I2. So there's my algebraic strategy. So I'll start with loop 1. So 13.7 I1 equals 12 minus 1.2 I3. So I1 is 12 over 13.7 minus 1.2 over 13.7 I3. I1 equals 0.876 minus 0.0876 I3. Okay, so there's I1 in terms of I3. Likewise with loop 2, I'll rearrange that to get an expression for I2. So 6.7 I2 equals 9 minus 1.2 I3. I2 is 9 over 6.7 minus 1.2 over 6.7 I3. I2 equals 1.34 minus 0.179 I3. Okay, so I've got I1 and I2 in terms of I3. So I'll put those in my current law expression. So I1 is 0.876 minus 0.0876 I3 plus I2, which was 1.34 minus 0.179 I3 equals I3. In this line of the equation, the only thing I don't know is I3, so I can solve this one for I3. So I'll leave all my numbers on one side, 2.316. Put all my I3s on the other side, 1.2666 I3. I3 equals 2.316 divided by 1.266 equals 1.83 amps. So there's my current running through this middle branch. I notice that my current is positive. That tells me I picked the correct direction for my current. So the direction of the current is as shown. Questions to here? This is just kind of algebra at this step. Okay, now we come to this equation and we find our I1. So we plug in I3 is 1.833 amps, or 83 amps. So then I1 is 0.876 minus 0.0876 times 1.83 to give us 0.716 amps. This one is positive, so I picked the right direction for I1. Okay, so I'm good with I1. And then I finish I2, 1.34 minus 0.179 times 1.83. To give me I2 is 1.01 amps. If you wanted another part of this problem, you could figure out the potential across each resistor. You know, V equals IR. I think we've done all the hard work, but you could do that step if you wanted to.
Miss?
Yep.
Could the current of that resistor be like the summation of the two source currents?
So the current I3 is the sum of currents 1 and 2, right? So I3 is 1.83. Which is close to what you get here. I probably have some rounding error. So I1 and I2 added together would give you this value.
No
Yeah.
matter what.
Yeah, because it has to be, right? Because that's what this statement says.
That's true.
Yeah. And actually that's kind of a good thing to bring up with regards to rounding error. Like I rounded a lot of stuff to 3 sig figs. When you have so many digits here, you can get yourself into a little bit of rounding error. So if your numbers aren't exactly what you expected, you can leave it and attribute it to rounding error, like if you're off by a small amount, or you can go back and use 5 or 6 sig figs. But just make sure you follow the process. Okay, let's do another example, and maybe that'll be the last one we do in class, because I recognize these are probably really boring to watch. Any other questions? Questions of the process? Make sense? So I picked this next one just because it's kind of an interesting question. So this is a used kind of circuit. Definitely people use these for different sorts of experiments. Find what resistance R we could put in right here to make the current through this resistor 0. So if we tinker with this resistance, we can actually make it so that no current at all goes through this branch. And when you have that kind of a circuit, it's called a Wheatstone bridge. I think for people going into engineering, you would see this in your circuits class. I think they treat this like a special section, like you'll do a unit on Wheatstone bridges, which is just this setup, right? So you make a circuit where you can, by careful choice of your resistors, make current through one of the branches 0. So let's apply our method to figure out how we do that. So we start by identifying the currents in each branch. We'll label them, and then we'll identify our loops, and we'll write down all of our laws. So we've got a 15-volt battery. We'll say that current comes out of the positive end. That's the first one we're drawing, so we'll call that I1. The current comes to this point. That's a junction, so the current has to split. So we'll say some of it comes out and goes down this way, and some of it goes down this way. I'm going to label those currents I2 and I3. I'm going to label the ends of my resistors, positive and negative. Okay, now this to me is sort of the interesting bit of the Wheatstone bridge. Current I3 gets to this point, and normally you would have that current splits. Part of it goes through the 85 and part goes through the R. But our special condition is that the current through the 85 resistor is 0. So there's no current here, so none of the current branches off. All of it has to come down through here. So to me, that's kind of the neat bit about this circuit, because the current in this branch equals 0. So no current is flowing through there. Likewise, over here on this side, I2 comes down. In theory, it hits a branch and it should split, but we know there's no current through that bit, so it has to come down through this resistor. So this is I2, the positive and negative ends. And then the currents recombine over here, come back up into the battery, I1. Everybody okay with the current labeling? Okay. So if we wish, we can go ahead and write down our junction rule right now. So at our junction, we've identified the net current in equals the net current out. Current I1 equals I2 plus I3. Next, let's identify our loops, and let's write our loop rules. So I'll pick loop 1. Loop 1, I'm going to take for this big branch of the circuit. I'm going to match my loop direction to my current direction. So here's loop 1. While I've drawn loop 1, I think I'll go ahead and I'll write my potential law for this loop. So loop 1. So as I come around the loop, my loop matches my current direction, so everything behaves normally. I have a potential increase with my battery, plus 15 volts. I get a decrease over my 25 ohm resistor. That potential is going to be the current times the resistance. So minus 25 ohms times current I2. Again, just so the equations don't look so messy, I'm not going to put my units in on this line. If you prefer the units, you may certainly leave them in. Then next in my loop, I get to my 12.5 ohm resistor. So minus 12.5 ohms times current I2 equals 0. If we look at this equation, this one is really nice. The only thing I don't know in this equation is I2. I think I'm going to go ahead and find I2. I wasn't asked for it, but I can find it, so I think I will because maybe it'll be important later on. So I2 is going to be 15 volts divided by 25 plus 12.5 ohms gives us 0.400 amps. Okay, now I know I2. If it's useful later, super. Okay, let's go to loop 2. I'm going to come around loop 2. I'll match the direction of current I3. I'll call this loop 2. And now I'm going to write my equation for loop 2. Here we see that things aren't so simple. My loops don't match my currents in every step, so let's be careful as we write our loop rule. Loop 2. I'll start with the 15 ohm resistor. My loop comes down in the same direction as the current. We go from high to low potential. That is a potential drop. So minus 15 ohms times I3 is the potential drop across the 15 ohm resistor. I get to my 85 ohm resistor. If you wish, you can put this in equation. You don't really have to, but the potential across this one would be 85 ohms times 0 amps. So no current through it, no potential across it. So put that one in or leave it out, kind of doesn't really matter. And then we get to our 25 ohm resistor. Our loop doesn't match our current direction. They're opposite, so we get an increase across the resistor, which we see as we go from the low potential to the high potential. So we've got plus 25 ohms times current I2 equals 0. This equation is nice because I just figured out I2. Now I can figure out I3 if I want to solve for that one. So I3 is 25 times I2 divided by 15. 25 times 0.4 amps divided by 15 gives us 0.667 amps. Okay, so far we're doing well. We're drawing our loops. We're figuring some stuff out. Let's come down to our last loop. We'll call this one loop 3. And let's see what our potential law for loop 3 will tell us. So as I go around this loop, my loop matches my current I3, so I get a drop across my own unknown resistor. So negative from my drop, current times resistance for my potential. So there's the potential difference across this resistor. I get to my 12.5 ohm resistor. My loop comes up, but my current comes down. I go from low potential to high potential. That is an increase. 12.5 ohms times current I2. You can put in your 85 or not, doesn't matter because the current through it is 0. If I look at this, I know my I2, I know my I3, now I can solve for my R. If you didn't solve along the way, what you would do is you would get to your equation for loop 3, you would recognize you wanted those currents, then you'd come back and solve for them, right? So no harm done if you didn't find them as you went. So our resistance R then is 12.5 times I2 divided by I3, 12.5 times 0.4 amps divided by I3, 0.667 amps, gives us a resistance of 7.50 ohms. So if you put that resistance in, there won't be any current at all going through this branch. If you change it even a little bit, you will get some current going through it. Any questions? Yeah.
Ma'am, why is the current in the 85 ohm 0? Like, can you explain?
Find the resistance required to make the current 0.
Oh,
That's how we set up our problem.
sorry.
Yeah. Yeah, so that was our starting premise. Okay, so I'll post more for a homework example. They all follow the same process. Identify your currents, write your current law, write your potential laws, do your algebra. So they all follow the same method. So, any questions before we keep going? Okay, we're good. So now we're going to come back to capacitors. We're going to put them in circuits with resistors. So we're going to make RC circuits. We're going to look at some of this stuff quantitatively, and some of it is going to be qualitative. So we're going to look at the behavior, and we will put some math behind it. So let's just do a very quick reminder of the circuits. So with our capacitors, we know how to make equivalents when we have series or parallel connections. With our resistors, we know how to make equivalents when we have series and parallel connections. So next we're going to move to putting R and C together and see what happens in those circuits. Okay, so that's where we're going. So I'm not going to do this in class because it's pretty straightforward. So I will say this is going to be a little homework project. Show that the units of the product of resistance and capacitance, so if you multiply an ohm by a farad, show that that works out to be seconds. I will post the solution, but that's something I'm sure you can figure out. If you want to have a look, the FET simulation for capacitors, so if you Google FET capacitors, it will take you to that simulation page. And we can play with it a little bit. So if I just connect a capacitor to a battery, we talked before about how when you hook it up to the battery, charge will flow, and then it'll flow onto the plates. We get one positive plate, one negative plate. We know how to find the capacitance from that. If we change the separation and the plate area, we change the capacitance. So that sort of thing happens. So what we're going to do next is talk about how do we charge and discharge RC circuits. So what happens if we take our charged capacitor and we hook it up to a light? Okay, so there's not a lot to this simulation, but it kind of shows that when you hook up a resistor or a light bulb to a charged capacitor, you do get current flow, and it does die out over time. So this is the sort of thing we're looking at. So a circuit that does get some current flow, and it does change over time. So for a little while, a capacitor will act like a battery. Okay, so that's what that simulation can show you. most of the circuits that you have in your life do have capacitors and resistors. So the thing about circuits with resistors is that they have a steady current flow. So if you have a circuit with a resistor in it, we know that there is steady current. And those are the things we were solving with those Kirchhoff laws problems. We hook it all up, we do an analysis, we can find what those currents are. Those currents will be the same forever until the battery dies. Okay, so we get a steady current. Capacitors, they introduce something new. We know that capacitors will either charge or discharge. So they have current for a short time only, and they do have a changing current. So sometimes it will increase to a maximum, sometimes it will decrease. So we only have current while charging and discharging. So what we use RC circuits for are circuits where we'd like to have currents, but we don't want it turned on all the time. We only want it turned on sometimes. One application I think is neat for this is your intermittent wipers, right? So you turn on your windshield wipers in the car, you set them to intermittent, they only come on sometimes. That's an RC circuit at work. It charges and discharges. While the charge on the capacitor is changing, we get current and the wipers turn on. Once it's fully charged or discharged, no more current, wipers turn off. So they turn back off and on. Okay, so first we're going to look at a charging RC circuit. That's going to be this one. Then we're going to look at the discharging, and we're going to ask about how that works. So I'm going to go through the charging capacitor circuit. We'll take our time to go through it, and we'll look at the details of it, because I think it is actually pretty important to get the function of these circuits, so to see how it works. So let's start. So we're going to do the charging capacitor circuit. In our circuit, we have a battery. It's got a net potential of epsilon. We've got a resistor with resistance R and a capacitor with capacitance C. We remember what the capacitance is, A epsilon naught over D. It depends on the features of the capacitance. So in the very beginning, before t equals 0, the switch is open. Okay, so this switch is open. If the switch is open, nothing can happen. Okay, we have a broken circuit, no current can flow. So switch open means no current. Capacitor is completely uncharged. Okay, so that's the beginning. Next, what happens is at t equals 0, we close the switch. So let's ask what happens at that moment exactly. So t equals 0, close the switch. So let's draw the switch closed. Now our circuit is complete. Once the circuit is complete, charge is available to leave the battery, charge can flow around that circuit. We can get a current flow because it's now a complete circuit. So the first thing we know is that current will flow. So let's draw that current, comes out of the positive end. There's our current I starting to flow through that circuit. Current flows, comes up through here, through the wire, hits the resistor, that's the positive end, that's the negative end, so charge is starting to flow coming around this way. Right at t equals 0, when the switch first closes, we can imagine one charge is coming out and starting to go around. So the thing that's going to happen first is that there is no charge stored up on the capacitor. That takes some time. So at t equals 0, that first positive charge can leave, but it doesn't hit the capacitor just yet because it takes an amount of time. So the potential difference across the capacitor, delta V for the capacitor, equals 0 because no charge has had a chance to get deposited on it. That means that all the potential is across the resistor, and we know that the potential across the resistor is current times resistance. This current, right at the very beginning, is the maximum current. And we say that I equals I0 at t equals 0. So we know current is only going to flow for a while. It is the maximum right at the very beginning. Okay, we're good to hear? Okay, well, what next? So this was at t equals 0. So now some little bit of time later, t greater than 0. So for some time greater than 0, the current has been flowing for a while. Charges are leaving the battery. Some charges are starting to build up on the capacitor. So some charges are building up on the top plate, some are leaving the bottom plate. The capacitor is starting to gain some charge, so there will be some potential across the capacitor. So at t greater than 0, the capacitor has some charge Q. The potential difference across the capacitor is charge divided by capacitance. That's just our relationship between capacitance, charge, and potential. There is current flowing through the circuit. So the circuit has current I. Now let's think about the details of current. We know that current flow is the flow of charge over time. So the current is the change in charge divided by the change in time, dq divided by dt. And then we'll make one special note that we get this current flow as the amount of charge on the capacitor increases. Right? So we go from 0 charge to increasing the charge on the plate. So I is the positive of the change in current with respect to time. Okay, are we good to hear? So we know the potential across the capacitor. Let's also write down the potential across the resistor. That's the current times the resistance. Okay, are we good to this step? So the next thing we'll do is let's analyze our circuit using Kirchhoff's potential law. So at some generic time t, which is greater than 0, we can draw a loop for our circuit. So I'll draw a loop that comes around like this. I will write my loop rule or my potential law. My loop rule says that my potential increase with the battery, and then I'm subtracting my decrease across the resistor, and I'm subtracting the decrease across the capacitor. It has to be 0. So I'm adding up all the potentials around the circuit. I get an increase across my battery, I get a decrease from positive to negative across my resistor, and a decrease across my capacitor. When added up, they all have to sum to 0. In your math class, or in Physics 2055, you will solve this equation. And when you solve the equation, what you find is that the charge, as a function of time, is the potential of the battery epsilon times the capacitance of the capacitor C times 1 minus e to the minus t divided by r times c. So you can either see that sort of a solution in one of your math classes. I have no idea which one. I don't remember what math class I learned it in. Probably differential equations, 30 something or other, I don't know. Also in Physics 2055, you'll go through that in more detail if you do that course. For Physics 2055, it is enough to know the form of that equation. Okay, so that's the expectation in this course. There are some special things to notice about this equation. First is this E here. Do you learn Euler's number in high school? Or is that in high school? Okay, so that's a familiar number to most people. E is Euler's number. .71828 Epsilon times C, so that's potential times capacitance. That's the maximum possible charge on the capacitor. In terms of notation, we call that Q with a 0 on it. And then the next thing we do is this expression here, R times C. We define a new thing. So we define, it's got a Greek symbol tau. So that's kind of like a curly T or a C with a little tail on the top. That's R times C. That's called the time constant. Putting all of that together, we get the expression for the change in charge, the way that the capacitor charges over time. So our result is that the charge on the capacitor plate as a function of time is the maximum charge times 1 minus e to the minus t over tau, so t is our time. So that describes the total amount of charge. When t is equal to 0, this expression is 1, the net charge is 0. When t gets really, really big, that whole term goes to 0 when we get the maximum charge. So that's our behavior. If we wanted to find the current in the circuit, we would use the fact that I is the change in current, or change in charge with respect to time. So we would take the derivative of this expression to find our current. And what we would find is that our current, as a function of time, is our maximum current I0, e to the minus t over tau. So we would do the derivative to find the expression for the current. With our current, if t is equal to 0, this whole expression is equal to 1. We get our maximum current. When t gets really, really big, this number goes to 0 and our current goes to 0. So that's the kind of behavior that makes sense for what we're talking about. If you wanted to find the potential across the resistor or the capacitor, the potential across the capacitor would be the charge divided by the capacitance. Across the resistor would be the current times the resistance. So you use your equations for potential to find those. Overall, the behavior of these circuits, if we think about how they're going, right at the very beginning, as soon as we close the switch, there is no resistance to current flow at all. This capacitor acts like a short circuit, so this current is a maximum right at the beginning. It's like we only have the resistor. At the end, no more current can flow because the capacitor is fully charged up. So at the very end, this thing acts like an open circuit. We don't get any more flow. So that's kind of what happens at the beginning and the end. Okay, that was a lot for one slide. Any questions? Makes sense? Hopefully it makes sense. Okay, let's make a graph of our charge as a function of time. And this should take you back to what you did in the lab. So we've been building the theory for what you saw in the lab. So let's graph the charge as a function of time for a charging capacitor. So this is the circuit back on the previous slide. We've got a resistor, a battery, and a capacitor that's initially uncharged. The amount of charge is given by this equation. We're going to ask what is the charge for times that are a multiple of our time constant. Okay, so we're going to pick specific times. So if t is equal to 0, so initially when t is 0, our charge at t equals 0 is q0, 1 minus e to the minus 0 over tau. That bit is 1, 1 minus 1 gives us 0. So the first point on the diagram is just a 0. That is not surprising. At the beginning, the capacitor is uncharged. We knew that anyway. Okay, so the equation backs up what we knew anyway. At our first time constant, so that first value of time, Q at our first time constant is QO, 1 minus e to the minus tau over tau. This is something we can put in the calculator. So minus t over tau, that's just minus 1. I can do e to the minus 1 in my calculator, do 1 minus that thing. What I get is 0.63 times Q0. So after one time constant, my capacitor gets 63% of the maximum charge. So that's about right here. Then I can do it at two time constants, Q at 2 tau, Q0, 1 minus e to the minus 2 tau over tau. Can do that whole bit in the calculator, and I get 0.86 times Q0. So we're getting close to the maximum charge now. I'm at 86%. Then I can do what happens at 3 tau. After 3 time constants, we get to 95% of the maximum charge. So here's our maximum charge Q0. After 4 time constants, we get to 98%. So up a bit right here. And then the special one is 5 time constants, 5 tau. At that point, we get to 0.993 times Q0. That's up here. If we connect the dots, do an exponential fit, we see that our graph looks like this. This 5 tau is a special number. We say that at t equals 5 tau, the capacitor is fully charged. Is that a true statement? Is it fully charged? No. No, it's not fully charged. How long does it take to get fully charged? Forever. Okay. So we have to pick some cutoff. When are we going to call it fully charged? Because we can't sit in the lab forever. The time we pick is 5 tau. Okay. The longer you go, the closer it'll get. But typically, we're pretty happy with 99.3%. Okay. So when I ask you on a test, how long does it take to charge the capacitor? If you're a smart aleck, you say infinity, I'm going to mark you wrong. This is the answer I'm going for, 5 time constants. Okay, we do have a couple of minutes left, but I feel like that's enough for today, so we'll quit there. And we're back on Monday, or Wednesday. Yeah, and we'll do more of this stuff on Wednesday, including the discharging circuit.